People can hear me online, I hope. Today I'm going to be talking about hyperabundance of endemic species, and specifically pink salmon in the Indian River and Alaska. So, start by giving a couple examples of endemic species becoming hyperabundant. Typically, in management scenarios, we think scarcity of endemic species as being a big problem, and we think abundance or overabundance of invasive species as being a big problem. But there are also examples where the species in extended range can become hyperabundant and unfound consistent where it lives. Two case studies are the mountain pine beetle and Pacific sea urchins. The mountain pine beetle is native to the western United States of Canada. Its life cycle destroys coniferous trees, and shifting climate has led to more frequent outbreaks as summers get warmer and winters get milder with rapid mountains. Pacific sea urchins, again, are native to the Pacific coast of the US and Canada. Their life cycle destroys top forests, and the hunting, the water populations in recent centuries have reduced natural predation by sewage, causing damage to the wildlife, causing damage to the forests, and returning more species for life. These two examples show hyperabundance of endemic species being driven by two somewhat separate causes. In the case of the pine mountain beetle, you have broad regional trends that may be rooted in anthropogenic activity, climate change, but they're not focalized in any one place or due to the removal of any one species, whereas in the case of some genus, we mentioned the hunting CRs, which has led to populations rising to the point where the list of the Gulf forest. So why am I talking about hyperabundant endemic species? Well, my research is focused on the Indian River, Pascagoula, and some national historical parks in Alaska. The Indian River is a small stream that hosts runs of 4 Pacific salmon species, including pink salmon, as well as a number of other resident fish species and anadromous fish species. Recent decades have seen a rapid increase in pink salmon run sizes in this river. There's a nearby hatchery which rears and releases pink salmon, and some managers think is driving the abundance of salmon. The question is whether or not this park and this river are experiencing an overabundance, hyperabundance of pink salmon, and if so, is it being driven by artificial trends or is it being driven by the activities in the nearby hatchery? This presentation will be in 3 parts. First, I'm going to provide some background on pink salmon in the Indian River. Next, I'll answer my first question, which is, are abundance is seen in Indian River unusual for the Rama region? Preview that answer right now is like somewhat. And if I'm running up against time in this presentation, then move quickly through that first question. The second question is, are the hunting releases driving the abundances of pink salmon seen in India? And the answer to the questions I'm not sure yet. I actually would love feedback and help with some methodologies to different problems and questions and test that. So first, a background on the system. I'm going to start with just discussing pink salmon in Southeast Alaska in general. These fish are very abundant and the most numerous salmon species in the region, both by numbers of individuals as well as by biomass. They also, compared to other Pacific salmon species, they naturally exhibit high rates of strength. There's some disagreement on how high which are in natural context, but compared to cohorts and pink salmon are known to spread easily from stream to stream. The Alaska Department of Fish and Game monitors pink salmon populations through fixed-wing aircraft surveys in order to keep an eye on the statement of the fishery. They have 714 pink salmon index streams throughout Southeast Alaska, including 35 in the recently designated northern Southeast Alaska, which is the neighborhood stream of interest. And this data is validated by randomly selecting a few of these streams each year to perform forecasts and to assess how close their area surveys to surrounding fields. This is a picture of what that data looks like. You're going to see this is the group escapement in each of the 35 streams in the neighborhood of 6 kilometer stream. But you can see here that most pink salmon index populations have seen substantial growth since 1990.
Right. I think you've told me this before, but what's the statement?
A statement is it's like salmon jargon. It means fish escaping the fish.
So they like were born in the fishery, but then they spawn.
I think that should Cole talked about my background in water economics. I think they use reclaimed to mean water that's not allowed to flow into nature. And in the same sense, it's just not allowed. They are allowed to not be fished.
Even with spawners, the ones who actually make it to the end game.
It's sold in it.
It's this game.
Uh, so this is the raw escapement numbers, scale per kilometer. And then my model is actually going to be looking at the log of escapement per kilometer, scale to the mean and standard deviation in the issue. The data that my models are actually going to show and look like. Next, I want to give us
Just out of interest, I don't see the funky. Do you have the normal pattern? Isn't it every 2 years? There's supposed to be a cycle.
So everything, that's a great question. Yeah, so pink salmon, they have a very predictable 2-year life cycle, so even long years that are completely genetically distinct. Everything that's flowing here is even.
Oh,
But in Southeast Alaska, the even year and odd year both see strong runs. So for the most part, like what I'm showing here, if I took the odd year runs, it would look for this one. So, some brief background on something else on this. Now, Indian River in specific, this is the most prominent geographical feature of that park. In time immemorial, it was a fishing camp for the Kissimmee clan of the Sitka tribe of Alaska. The river is supported strong pink salmon runs into the 20th century. Plinkett elders recalling that they were using the time to walk across the stream on the backs of the pink salmon. They were numerous. And in 1939, gravel removal to support the building of fortifications for World War II decimated these salmon runs and led to a number of large flooding deaths in the river valley. Salmon runs were low for a number of decades after that. And meanwhile, the Southern Texas hatchery began operations. This is a not-for-profit educational hatchery, which releases 3 million pink salmon per year. This aided initially in the recovery of the pink salmon run in the river in the 1970s. And this hatchery is the additional twist of drawing water from Indian River. It actually owns enough water right to water from upstream. And so they use the same water from Indian River to pink salmon, as well as they release a certain amount of water into the harbor when pink salmon are returning in order to attract it back to the hatchery. And just for context, here's a map that shows the amount of Indian River there. And those are some of the hatchery. These are about 1,700 Chicago ocean line to so it's just the next one pretty easy for them to gain from one and this and since 1990s, pink salmon populations added in the river and increased dramatically. And the question then is this an unnatural hyperabundance and what would the implications of that be? Now, these large numbers of returns, when they spawn, die, and decompose, all those decomposing pink salmon deplete dissolved oxygen in the stream. These flows this occurs at a time when flows are typically late during the later flow during the late summer. And so all those decomposing bodies can really have a heavy effect on the salt oxygen levels in the water because there's already less water to begin with. And these are potentially fatal hypoxia events for other species which depend on Indian River.
what species are those?
There's some other specific salmon, but those are anadromous, but then there's Dolly Varden char, there's sculpin, there's herring spawn in the mouth of the river in the spring. There's rainbow. And then there's also all the transient species that are very species. So, two scenarios then are these abundance or hyperabundance of pink salmon being seen in the Indian River, the result of broad regional trends, like we're seeing these not all over Mississippi, or is it partially or entirely due to the direct intervention of the hatchery dispersed? 15 minutes in, so I will move quickly through this first question, but the question is where does the Indian River fit in this picture? The raw data that I've got on the Indian River looks like this. You can see there are gaps in the time series, and this answer, it's not, doesn't feel complete. It's saying something, and from looking at this graph, it seems the Indian River isn't very out of line with what's going on elsewhere in the region. I'm wanting to take this a bit further, using Mars modeling to try to get estimates of the unlocked state, both the pink salmon history elsewhere in the region as well as in the these models allow for gaps in the time series. This is a good advantage because gaps in the time series don't get around. We also allow the treatment and abilities time series drawn from some larger underlying state, so all the gray streams there are going to be treated as samples from the large underlying state, which is based on in northern southeast of us. There must be.
Then you have like data and your symbol, I thought you were like having like. Well,
Lines are coming from these ADF and G index surveys, but the stream in the park isn't one of their index streams. So they've surveyed it irregularly over the years. I mean, it's kind of in their territory, but it's also National Parks' responsibility to conduct these surveys. And because of the hatchery operations, they don't see that as a useful indicator of what's going on with the fishery in general. So we don't survey that consistently throughout the years. These models also provide estimates of the variance and year-to-year change in the underlying state. So here, this is where the variance of those 36 streams, including Indian River, lies between 0 and 0.03 about. The Indian River is on the very low end of that spectrum, but it's not an extreme outlier.
This is variant, what variance is this between year variance?
Then there's variance in the year-to-year change that the model is estimated.
The process error.
Yes, yeah, the process.
That looks odd.
Okay.
0 for a process error usually means you got a convergence problem.
So linear regression.
Sorry?
It's just a linear regression. The line is entirely stop shimmy rates, so process models. It's basically a biased random walk with no.
Right, but I mean, there's presumably no signal. 0 doesn't make sense.
Yeah.
I mean, you probably don't have enough data to. You haven't got a hierarchical structure on your sigmas of any kind, or do you?
Yeah.
Yeah, I mean, that's when I see a 0 process error, that usually means it souped up all the signal into the.
Just absorbing it.
Yeah, it's just basically saying it's observation error, not observation and process. So I'm trying to think who did this for Thomas Buren. Doing it Bayesian with a prior on the between stock variance. It's made to avoid these extreme versions, but I don't know if that matters.
Everything scaled was to per kilometer and it's all relatively small radius, it just assumes it's like.
Yeah, I mean, yeah.
Which I believe is something.
So these models with short time series can, they're not well defined for estimating both process and observation.
Make them over.
Well, it's just that you can't detect it from that view. You're estimating a variance. I mean, I tend to think of variances as F distributed, and think of an F distribution, and it's not a very nice thing if you don't have a lot of degrees of freedom. So estimating process error is just bar normally, and with 20 data points, it's very
Okay.
okay.
Yeah, I'll follow up with you on that after the lecture. And looking at this underlying state estimates, didn't have that also more than maybe a little bit than the underlying state of the unbelievable stream in terms of so we see that the error bounds around the individual larger. It's not that academic relative to the others, but in general, it's behaving similarly to what we're seeing elsewhere in the region, although higher. So the system seems a bit unusual in the context of the broader region. And the implications then are that pink salmon abundance, like the pine mountain beetle, may be due to regional trends, but like with the Pacific sea urchins, it also could be being pushed somewhat higher than average due to hatchery releases. The complicated management challenge and the question what impact with conditions and what role the hatchery is playing. Which brings me to the second question that I'm interested in, is how these hatcheries formally this hypothesis and one of the interpreting idea the Sheldon Jackson hatchery is impacting the abundance of big salmon in the Italy River. This will require estimates of Indian River statement. It'll require data regarding strain rates to and from Sheldon Jackson hatchery. This is the piece that I should like to get people's feedback on. And it'll also require some additional control. So, as we just discussed, my Indian River escaping data, there's gaps in the time series. But I have these marginal outputs that are estimating the underlying stuff. So, as conceived at the moment, this is what we're going to use as a Andre doesn't like it. This is what we're going to use as a variable.
They're on data,
Okay.
and you surely analyze data. These are model outputs, right?
Okay.
So they're not independent, they're not, they're not data. You really should analyze data.
Mm.
You know, it's the things that you measure. I mean, you could build interventions into Mars models, right? So you could put a covariate in a Mars model to say the process error, I think C, was it C? I can't remember.
Yeah.
Whatever. So there are better ways to do it than taking this as output. It's very convenient because you get a lot more data points with this than you had in the original data set. But it's cheating.
So, we'll have to talk about it. No one's.
Well, as long as two reviewers are okay.
Well, let me ask you this then. Let me give you some down on this variance because I'm trying to represent stray rate information. Now, this is also the stray rate data is sparse and it's messy. It's a picture. It looks like it looks ugly, but all in all, I've got 38 good sampling efforts between the Indian River and the hatchery, taking in more than 20 fish at a time, checking over the homeless margins, and seeing whether they ended up with first stand up or whether they ended up in the wrong place. Two major issues here. One is that there are only 10 years between 2011 and 2024, with some data involved. And only 7 of those have sampling occurring at both sites within the same year. That looks like this, where the y-axis is the percent of fish that are marked in each place. So the pink polygons show hatchery fish arriving in Indian River, whereas the blue polygons show hatchery fish arriving where they're supposed to at the hatchery. You can see in some years the percentages are real low for both, and in other years the percentages are really high for both. Part of the reason that could be occurring is because these data, they're inconsistent in the timing of the sampling. So not all of them are coming from different, but these samples are occurring in different times in the hatchery is drawing its sampling from cost recovery efforts as well as collecting meat stock, but following the new release, sampling comes to the season, where sampling in the park has been later on into September and October. So it's really not germane to compare 2011 to 2011 because one of those months could be October and another might be sparse and messy, and I'd like to, I need to have streaming data or at least synthetic streaming data to say something about if that strands out of conservation apart. How best to address this lack of information, we're kind of considering, Mark and I, my advisor, kind of considering 2 possible scenarios. The first is a Bayesian approach to generate synthetic strain data. This would use literature to inform priors and use that available data that just going to use to inform livelihoods. The second would be just evaluating range of potential stray rates based on what we're seeing happening at those sites. And this is where I have a lot of suggestions or feedback, even now or after the talk. But this is kind of like the step that we're on in this work is figuring out how to construct that stray rate data and it's not cheating, but informative. And the next steps after settling on an approach to accounting for straying would be there's a potential to include stream level characteristics in that larger Mars model. There's a lot of digital models where we're pulling more characteristic for all those different 35 streams and not just and another potential piece of this work is once we have an idea of what the straying is happening on the escapement, assessing a few potential management actions and seeing if we can stab at what impact those management actions might have in the system. That's where we've been so far. Okay. So.
You like Brian, you look that the plot that you showed with the fitted line for the Indian River compared to all the other states of line, that must not be for the same thing because clearly it was some awesome in
Because the shot it, a lot of people are the same thing.
Yeah, well, that's estimation variance, right? That's not process variance.
You're talking about this guy right here, right?
Oh, there's variance.
I think that's the estimated.
Yes.
It's not the straight line, it suggests there is processing. So I'll have to go back and look somewhere this is.
Well, okay, we'll compare. I mean, the variance term isn't a pure 0, but it's very, very small relative to.
Also, so you've got to be careful because it's also drawing lines between things. There's a whole lot of gaps in here, and so it's, you know, it's not like a full state space model. Or it's a full state space model, but you don't have data in all places. One suggestion would be put the little dots in where the data are, so you can see where the model is drawing line. There's straight lines there where if you break it down, it just sticks a line.
I mean, the only covariate I was able to feed this was like specific to the oscillation, so in those places where there were blocks and that's sort of all that's gone, so it's not violence.
I mean, quick, actually, just realized I'm going to mathematics. Obviously, mathematics. But a couple of things that you may already have done. One thing you can do with a state space model is treat your stray rates as that's another time series in principle that you could model in the Mars model. Not totally sure what transformation I would do on percentages, but yeah. And then the other thing is, do you have data on releases of hatchery fish at the hatchery? Because that's presumably the biggest piece of information you're going to get is if there's a contrast in how much hatchery fish are going out. Does that then, normally what you do is you'd say the process error is related to some covariate, because that's what the model tries to explain. You've got no process error, so it's sort of doomed at the moment. But if you've got, well, you're saying there's nothing affecting. It's just as Mark said, it's a trend.
Right.
But if it's just a trend, there's clearly that's not being affected by anything. Otherwise, it wouldn't be a trend. But what you're looking for, if there's contrast in the hatchery releases, then
The releasing the time.
don't know enough to, well, there could be some contrast in the treatment so that you can then say, can you see it in the data?
Cheap place to look, I mean, I know that over the years, they've increased the number that they release, but I think that goes kind of some points where,
As long as it doesn't flip, because then you have no signal. So those are the kinds of, and the other thing that I really do, and this is painful, is a simulation study to detect, would you in hope and hell of picking this up? So the difficulty is some type 1, type 2 problem, right? Most people worry about type 1 error. I think given the number of data points, your problem is type 2. In other words, there is an effect, but with only 20 data points, you'd never be able to detect.
right.
Brian knows all about this. How we doing fallback rates? Rockfish assessment. He's still alive. He was almost crucified yesterday. The nails, you've taken the nails out. I was in a different meeting. That's fine.
Can you go back to that plot of the red and the gray line? I guess so. What you are looking at, the difference between the red and the gray here, to see if it's different from the general. Since the gray line, is that just an average of all the other locations, basically?
It's an average of all the other locations that the model is considering in hand with who made the observation. So I have data on the observer. A lot of the observers are unknown, but where I can, one of the purposes of these models is to disentangle observation error from process error. So that first equation is where you're feeding your observations. Second equation is trying to predict the process based on those observations.
Yeah.
So I have information on observer, and that goes into that observation equation. And I have what goes in on trailing. Certain thermal oscillations provide some measure of ocean climate when these fish would see, and it's all by a year because it's many of them not seen before. So the spawn freshwater. But for that widespread model that's considering all those 36 streams, those are the only covariates because they have temperature or flow rates or weather for all those individual streams throughout the broader region. Now, again, it's like there are these visual exposits that allow to pull some more of that in, although you would think the topography of the streams, while it is changeable, isn't changing dramatically from year to year. Yeah.
So are you basically assuming all of the streams are independent of each other?
Yes. Yeah.
Is that are any of them connected or tributaries of the same?
No, so these are EF and G considers them all being populations.
Cool.
Yeah. It's just options in the systems and stuff. In
You can estimate parameters of Q to examine that. I mean, that's what Terrence has done for his. I mean, that's where the Q is the variance covariance matrix for the process error. And
then it can the model can estimate how
correlate, yeah. You don't estimate N by N, you do something like correlation as a function of distance. And in Southeast Alaska, distance is very complicated to calculate. Now I think about it. Two places can be that far apart, but the actual distance is Yeah, so I mean, I would, so you can do that. Again, I haven't simulated it, but the ability to estimate variances is hard. The ability to estimate covariances is even harder. So when I'm
That would be adding like more or less degrees of freedom to try and like. Yeah, have some covariance.
Matrix. I mean, it's less degrees of freedom, but not to a degree that I think would crash the model. It's a lot longer for each one. What's that more
exactly.
Yeah, hopefully less little CT here times bases like most of that.
Exactly. And R will be diagonal if we've got a decent software place inside. But yeah, I think a simulation study to ask what can you estimate would be before you spend a lot of time trying to solve a problem that actually is insoluble.
Given the paucity.
Yeah, in other words, what could you detect from a data set of that length? I mean, my experience estimating, Mark's got far more than this than I have, but you need hundreds of years of data to get things like covariance. It's just, you need lots and lots and lots.
In the case of all those other stores, the same thing in Brainerd, I'm not the one. So Brainerd, rights, well, you know.
Oh, no, it's not criticism either. It's not even
If any of the G's is sort of to move those are all these things in the independent civil populations, and like I'm willing to assume independence from the assessment. Comes up thing, I'm not things. I think, but it's way to proceed.
Yeah, like I mean, that's right. I mean, usually it doesn't make a huge difference that there's correlation. It just means that you can refine some of the trains that are poorly solvable. So what you're really hoping is your stream is correlated with something else.
Yes.
That would be easier.
Do you have a question?
Yeah, I was wondering if you could just tell me what all the different on this.
So I can try my very best. YT are your observations.
Yeah.
The Z on the XDs then are kind of a like time variable in your observations. The A and the U, please somebody interrupt you.
I mean, this is just a global stuff.
They can like move the modeling across the standard, just like randomly like walking back to the same. The D and the C are the effects. The little C and the little D are where you would include the other things.
Yeah, what are they?
In the model that I showed, the only thing they have for little d is the observers. So the individual that made each observation, measured as like factors. And then little c is the cyclical oscillation that reflects or measured ocean climate. And it's lagged by 1 year. So that's the time it's been sound. Okay. And the W and the essentially the fractions.
Most of these would be one, right? So
Most of the ones are.
yeah, X would be a diagonal matrix, so you can forget it. H should be a diagonal matrix, so you can forget that. So there's a lot of matrices. This is a super general version.
Yeah. This is
Most of this version, especially in log space.
For at the problem of different observations,
Mhm.
about in the D matrix, and then maybe put five or something on the bars, 3 and 1.
Quite possibly, yeah, but then you would be estimating the stray rates of these Mars models and then including those estimated stray rates in further,
One model.
like hierarchical model.
Yeah.
Okay, yeah.
Don't ever create data. There's a huge temptation of putting a time series of stray rates and then creating stray rates and putting them as covariance. That's
You have to, I came from economics now.
it's not here. You trickle down and swing rates.
Yeah, thank you, Brian, so much.
I wonder if it's my comments on it.
No, but I also see your question. I'll try to follow up with Brian and get you an answer for that.
I'm gonna send you an email. It's fine.
My office is next to his, just about.
Good stuff.
Actually,
They're gonna be first.
Oh, what's the, yeah, wow, I thought you were taking the day off. I was listening. Oh, wait, it was pleasant. Glad that I know Brian presented the callback, first pass of the callback assessment yesterday. Got more comments than Philip.
Just thinking. And since all the way is a lot of when like said the work, it's what I was saying. Just nice. I was a longer walk than I expected.
That's, we're talking about distances. Straight line doesn't get you to Northwest. Yeah, I'm telling you. I don't know, so I don't think I've seen you or something.
Yes.
It's just a short thing. The problem is, it works well today, so you got to long.
I don't see. If you go with the.
There's your, just,
And the answer is very similar.
yeah, I'm getting.
Translate that on Thursday and I don't know.
I'll do a quick introduction for Michael. So Michael Kinneen is a master's student in the Punt Lab at the School of Aquatic and Fishery Sciences at UW. His research focuses on model diagnostics for stock assessment, simulation testing, and breaking ADMB, and recently TMB, all DAS models. Before coming to SAFS, he received a bachelor's in science in marine science from the University of Galway and worked as a fisheries analyst and survey technician in the Fisheries Ecosystems Advisory Services team at the Marine Institute in Ireland. And Nico asked if questions could be held until after the talk.
So that I'm left.
Yeah.
In the interest of time, we actually might be better off taking them as we go, just so that might be a little bit, so. Sorry, for putting you off, but feel free to ask as you go.
Yeah, go ahead.
Great, thanks, Cole.
Thank you.
So my talk today is going to be on the second chapter of my master's thesis. You try to use mean absolute scale there as a diagnostic for misspecification of stock assessments. So quick background, why do we care about misspecification of stock assessment? When a model is misspecified, it means that it's no longer accurately representing the system that we're trying to model, or our perception of the system we're trying to model. When this then means that key quantities of management interest, things like terminal biomass or harvest rate are incorrect or misleading. And then when we set management actions based on those quantities of interest, we're not applying the correct management action. And this can, in extreme cases, mean something like collapsing the stock or having to close a fishery, or just having unrealized cash. So to offset this and to make sure that or try our best to make sure that our assessments aren't misspecified, we apply a suite of diagnostic tests in the hope to be able to identify the misspecification. By applying a range of tests, you can test different components of your model, and you also reduce the probability of a misspecified model slipping through the more test cheating. And these can be things like using age-term production models, catch curve analyses, lifetime models, or any combination. The mean absolute scaled error, the statistic that I'm looking at, is the error metric from the time series literature, and all it's doing is assessing the predictive ability of the predictive error of the model of interest relative to another baseline model. Traditionally, they use a naive model. Naive model just means that your prediction at time t+1 is your observation from time t. So you're just assuming your system isn't changing. And the kind of key advantages, part of the reason we're interested in maize is that it's firstly that it's scale free. So even if you're comparing two models with vastly different structures or different data, the comparisons hold true. It also means you can calculate it for different quantities within your model and compare those. So how well you're fitting a certain index or the mean age or length of your catch. It's also very easy to interpret. A maize score of 1 means your model is exactly the same as the baseline model. Greater than 1 means your model is worse than your baseline model, and less than 1 means your model is better than your baseline model. And I think in fisheries, having a statistic, or in fields of stock assessment, having good interpretability or simple interpretability for statistics is great for kind of communicate with decision makers or stakeholders or other scientists. And the third aspect makes it interesting, or that's desirable compared to something like mean squared error, root mean squared error. It's much more robust to outliers. So even if you have very extreme values in your time series, the distribution isn't going to skew as much as you would expect those other statistics. Now, maize is already being applied to some degree in stock assessment as a measure of predicted skill. So this is just to assess if the model forecast is improving on that from a baseline prediction. And a note in this is that while traditionally we use the naive model, and where it's been applied in stock assessment, we've used the naive model. There's nothing stopping you could use a benchmark model in there, or if you're testing between models, you can change the model in the denominator. So just to walk through it, your H term is the number of steps you're assessing the forecast over. And capital T is the terminal year of your time series. Y tilde is your model forecast. YT is your your data observation at time T, and then T-1 is your naive forecast. It's -1 just means we have a forecast horizon of 1, which means we're just projecting the model 1 year into the future. Or our naive model is just going by 1 year at a time.
All those brackets supposed to be absolutes, by the way, the top in the numerator.
And they are supposed to be absolutes. No, that's correct. That's nice. The absolutes down there. Yeah, there should be brackets. So it should be the absolute value of the prediction residual versus the naive residual. Thanks for that.
I should know that, but
I should definitely call it. Yeah, and we can calculate maize for any observable quantity within our system. So again, if you wanted to do for your model fit to index or your the mean age of the fishery composition or the survey composition, the issue we run into in fisheries is that a lot of the quantities we're really interested in, we've never actually observed. Right? We can estimate them and we can say I have a great model and I have a really good estimate, but going out and hatching every fish in stock and then seeing how our model actually compares, we can't do that. And as interesting as that would be for ground truthing, there's obviously no federal laws, no actually.
I have a question around the formula.
Yeah.
If you have a 1/h in the numerator and the denominator,
Mhm.
that's
Correct. So yeah, so what you're ending up with, it just means that the number of forecast steps that you do in your numerator, you're making an equivalent number of naive forecasts in your denominator.
I mean, physical.
question. Yeah,
Right.
You don't need one.
No, I've never. Well, yeah, I agree with this. Sorry, but yes, good question. I should do that. Well, yeah, so with hindcasting is this process in fisheries that allows us to generate observed quantities where we don't have them. So in a hindcast, we fit a model to our full data series. We then truncate that data series, refit the model to the truncated data and project both series. So it's similar to a retrospective analysis, but you're projecting the model over the data you get. So this would be just it is kind of thought here. This would be if h were equal to 3, we would have 3 terms in the numerator of comparing y tilde capital T to YT, y tilde 4 to Y4, and y tilde 3 to Y5. And then the naive predictions for the denominator would simply be y capital T -1, Y4 -1. So the key question that I'm really interested in looking at is maize useful for detecting and identifying model misspecification in integrated stock system models? So to explore this, what we really want to look at is we want to look at different misspecification types. So is it sensitive to misspecifications in different parts of the system, parts that might relate to the population dynamics, the observation model, or the data weighting? We want to see is it robust to patch histories. So different stocks are going to have different exploitation patterns, and are there cases when it is useful or cases when it isn't useful, and different life history patterns. So can this only be applied to stocks that fit within certain bounds of small pelagics that grow super fast, or fit within a long time? So to do this, like, the simulations were conducted using SS3 Sim, which is an R package that allows you to do simulation work using the stock synthesis assessment model. And so starting on the top left-hand side, for a single simulation run, we start with our operating model, and this is where we specify this is the things in our system. So the dynamics within the operating model are, the model truth. We then use stock synthesis to generate data according to the truth, and then we sample from that data with observation error. So the output of the OM data would be perfect data and very unrealistic. We apply our observation error and come up with a sort of a realistic data set. That's then fed to the estimation method, which is simulating an actual stock assessment, and that stock assessment is fed to that data file. So this is conducted for 6 models, one over the full-time series, and then for each number of retrospective years, so the number of years we've updated the data set by. And then for each one of those models, we have 100 iterations.
So you would take the data with your observation error and just truncate it a year and run the estimation model?
Correct, yeah. And so within the iterations, it's where, for the simulation purpose, we introduce the process error to kind of create this stochastic system. And we do that by setting a series of recruitment deviates for each year in the model. And while we have the key thing with the recruitment deviates is they differ between iterations. It's a different amount of process error, but they're consistent across scenarios. So iteration 1 in the full model has the same amount of process error, the same pattern in the recruitment deviates as iteration 1 for the retrospective 1 model, or iteration 1 of retrospective 2 model. So the data that we're using in this,
iteration is this another simulation from your operating model, right?
yes,
Different iterations to simulation.
different iteration. Yeah, each iteration within a. Sorry, what's the question again?
You're just simulating with your operating one every day. I don't know. So, I think it's
Okay. For the data that we're using in this simulation, we have 2 fleets. So we have a fishing fleet, which has catch data from the beginning of the fishery in year 25 or year 26 up to year 100. The fishery begins in year 25, but the model itself runs from year 0 to 100. And the first 25 years are kind of used as a burn-in period. So we have catches for the entire time series. Then we also have length and age compositions from the fishery. And the frequency of collection of the data and the amount of data collected ramps up over time. So this is kind of trying to emulate a typical fishery where you don't have much sampling in the beginning and then you increase that over time. Then in 1975, we have an index survey beginning. So this gives us an index of abundance, an index of abundance biannually from 1975 to 1990, and then 90 to 100, it's the right kind. And then this just has a fixed quantity of image length composition and composition data for each year.
So it's signing off, gotta go.
There. That's that.
I think Ryan's gonna get up, walk out, but given the amount of simulated data you got here.
It's the obstacle. So then in addition to, from the data, we want to these patch scenarios we want to explore. To define these, we start with a yield curve for our speed, in this case, thought. And from that, we estimate 3 reference points, our FMSY, or our fishing mortality rate results in MSY. And then FI, which is fishing mortality rate, results 85% of MSY above MSY, and FLO, which is 85% below MSY. For these three reference points, we define our catch patterns. So the first is just what I'm calling the flat pattern. And this just means once the fishery starts, it fishes in MSY every year, or fishes in FMSY every year until the end of the simulation. The linear pattern, which means when the fishing rate ramps up from 0 to FI in the final year of the model, and then F2A, where there's a linear increase to FI until year 85, and then a linear decrease to FLO in the terminal year.
Because our FLO and FI pretty good yield ranges, this is 0.85 MSY, it's that in from.
It's derived, so I based it on this Ono et al. Paper, who did a very similar simulation setup. I think pretty good yield, 80%.
That's right.
Like, don't be wrong. Yeah, so this is just, I based a lot of the setup on this Ono paper, so they can be kind of compared in between. Yeah, so the three life history patterns are kind of this trade-off between growth rate and the longevity of the species. So at one extreme, we have Pacific sardine, short-lived, super fast-growing. In the middle, we have Atlantic cod, which is kind of a medium growth rate and medium longevity. And then at the other extreme, we have a Pacific halibut, which is this very long-lived species that grows quite slowly. For sardine and halibut, the operating models are parameterized based on the most recent assessment available, and then for Atlantic cod, it's based on this kind of defined operating model in simulation literature. The estimation methods that I'm looking at, then we've 8. So the correctly specified model, this is where our estimation method matches our operating model. So this should be the determining dynamics. There are 3 groups of misspecified models. So systems dynamics, or misspecifications that relate to the population dynamics in the system. In this case, the misspecification of natural mortality, steepness, and then where natural mortality varies over time, but is finally varying in the operating model. Then I have 2 relating to the specifications relating to the observation model. So in the operating model, we have asymptotic selectivity, and in this misspecification, we have dome shaped, and then also a hyperstability scenario where in the operating model we have a linear relationship between the survey index and biomass, and in this misspecification that's non-linear. So our catch rate in the survey is staying high, but our biomass is declining quicker than the surveys infer. And then we also have 2 misspecifications related to data weighting within the model. So in these, we increase the weight in each of these models, so for the age composition or length composition data, to 10 times the weight it's assigned to those data sources in the correctly specified model. So all these misspecifications break the model in different ways, but even though we're breaking it in different ways, we want to make sure that it's the same level of broken across scenarios. So to do this, we estimate the depletion from the correctly specified model, and then use a bisection method that finds the parameter value that results in a median depletion of CSM depletion value plus 0.05. And then those EMs for the simulation are fixed at that value. Because altering the weight assigned to the compositional data didn't have any effect on the depletion in our model, I just set it based on 10 times the value, the weight assigned in the correctly specified model. 10 times is probably quite a large effect, but from kind of conversations we had, we didn't really expect it to be detected. So start with a large effect, and if it detects it, we can work back from there. And this is just showing the results of this bisectional analysis. So we're doing one of the fishing patterns. You can see on the far left, we have our correctly specified model with lower depletion, and then equal depletion across the different estimation methods. And then
Sorry, can you go on one more slide? So I thought you were matching the depletion in your specified models.
yes, So each misspecified model has through depletion plus 0.05. Yeah, sorry, I don't know if that's good or not. Okay. Yeah, and so this is just kind of an overview of that, of what the whole simulation frame looks like. So for each life history, 3 fishing patterns, for each fishing pattern, 8 scenarios, and then for each of those scenarios, we're calculating based on feed quantities, index of abundance, CPUE, the mean age of the catch, and the mean rank of the catch. For in the interest of time, I'm just going to focus on the top results. So just kind of starting to build up these results a little bit slowly. On the x-axis, we have the number of time cast steps. In this case, it's just 3. And this is for a single patch scenario, it's the 2-line pattern. And then the colors we can see are the correct one is the blue is the correctly specified model, and the yellow is our misspecified model. And the reference line of 1, again, there being greater than 1 means the model is worse than that naive made model. Less than 1 means the model is better. And 1 has also been used for where maze has been used for assessing prediction skill as the kind of the pass fail point for the test. So if it's below 1, it'll pass the test, below 1 it'll fail. Yeah, so then we expand this, it's the same block, just expand it to the 3 different fishing patterns. Seems it does change small but flat, but what's really interesting is that with the linear pattern, the correctly specified model is actually getting worse than the misspecified model is getting slightly better. I'm not entirely sure why.
I'm sorry, one question.
Yeah.
What is the naive model again? Like,
So the naive model is just saying the prediction from the naive model is the observation for the previous taxon. So the naive model prediction for 2025 would be the value we observed in 2021.
Gotcha.
And then we expand this to look at the misspecifications under a different number of time pass steps. So this is how many retrospectives we're averaging over for the statistic. So this is for the first set of misspecifications for the systems dynamics. And you can see that there is some sensitivity, particularly to natural mortality, where misspecified natural mortality and time varying natural mortality, and that's kind of the pattern that we would like to see is that it's generally this median value across simulations is below 1, but a correctly specified model and above it for misspecified models. Yeah, but then for EM2, where we misspecified selectivity in red here, we can see that it's the model isn't really detecting at all.
So can you go?
Stevens. Sorry, that was selectivity.
Yeah.
Sorry, it's misspecified Stevens.
How big are the error bars? Are they 95%?
Error bars are 90%.
90%.
Yeah. This is for our observation model, so kind of even less sensitivity. Within that, there is some change. We can see, beginning with the reduction in error, for the incorrect selectivity shape, which kind of indicates it's actually performing better than the correctly specified model. But again, hard to kind of differentiate a true distribution from a misspecified distribution within that. And then for the data weighting scenarios, they're just identical. The model had, or the maze statistic had no ability at all to detect that. Yes, the maze distribution, the maze showed some sensitivity to misspecifications relating to natural mortality, but none for steepness. It's unsuitable for the detecting incorrectly weighted composition data. Now, this was in the Ono et al. Paper, they found that the composition data is much more important to the short-lived species than it was to the long-lived species, or the longer-lived species. So it'll be interesting to see what the data weighting plots look like for the sardine. And then, yeah, the distributions for the observation models weren't distinct from the correctly specified model. And then these results, I've only shown these plots only refer to maze calculated on CPUE, but it's very similar. It's similar patterns across the mean age and patch and mean length and patch patches. So overall, with the exception of natural mortality, maze distributions were not We're not conspicuously different for misspecified models, correctly specified models, which indicates probably not great as a diagnostic. Because of how much the distributions overlap for the correctly specified model distribution and the misspecified distributions, it means that you can't easily define, based on a certain maze value, you can't say, okay, we think this model is misspecified or correctly specified. And I suppose kind of what Andrea was saying earlier about, you know, both very high type 1 and type 2 variant. And this is similar to results from one of Maya's papers, where she also found that there was a high pass rate of 55% vertical and equal pass rate, even for depending on specified models. This trend seems to be, this insensitivity seems to be similar across model structures. This paper by Lee et al. Found that maze was insensitive to a range of specifications, with the difference being they looked at space-based models. And then the variation in maze distributions across fitting patterns to me seems like it might also be mirroring some of the stock response to the explanations. So for the next steps, I need to expand this to the sardine and the halibut model and see how the distributions look over those. Boy, with different forecast horizons. So instead of just having a -1 in the naive model, you're looking at -2, -3, and that's how far we're projecting. And then also, this is as a result of my last mini meeting, Nadine brought up using an inverse weighting approach or a weighting approach to maze. So currently, all the CPU data points just have a sigma of 0.1. But if they had variable CVs, and then we weighted maze based on those CVs, how would that look? So you're assigning a higher weight when the model fits a low CV data point compared to a high CV data point. Yeah, and with that, I am happy to take any questions. Sorry, I kind of blasted through that, but sorry, so I can find.
Hard to use. In what? Operating model.
Sigmar, it's species specific, so pretty odd, I think it's 0.6 odd.
So in the case of the linear F, does it successfully dampen out the variability and does the population pretty much stabilize?
Yeah.
After a few years?
Yeah.
Which is potentially that's why you're not seeing anything in the. You're not seeing a difference from one, because if your population's not changing, the CPU you can see every year.
Naive predictions.
You prevent speed they never did the naive prediction, right? That was wrong every year.
Yeah, that's what happened when you look at I don't have the plots here, when you look at the kind of spawning biomass and the age compositions of that linear pattern, there's so little data about that. It's just, yeah, exactly that.
Yeah. You're using this in simulation context and therefore. Yes. What do you foresee the application of this outside simulation on actual assessment?
So when I started on this project, what we were hoping to see is if we could find clear distributions between correctly specified models and incorrectly specified models, we kind of set breakpoints or indicator points similar to what we have with something like Mullis Row, and say, okay, if a maze is above 0.1 or 1.1, it's a cause for concern. Given these results and the inability to define that, I'm not really sure how you apply it in context. But I'm hoping that once I run it for multiple history patterns, inform that a little bit more and have more of my data. I would say how it needs.
Yeah, so I'm wondering about your naive model, so I just want to make sure I have the first part right. So in your naive model, your next prediction is your next prediction is the same as the observation from the previous time set, correct?
Yeah.
So I'm wondering can you modify that in a way? So I'm thinking of a scenario where you've done a bunch of assessments in a row and you watch the population steadily decline like in a one-way trip. Does it make sense to fit a linear model for all those and assume that have your naive model be something like, we're assuming it's going to keep going down because it's been going down for the last 15 years at a steady rate? Or is that very explicitly not what MACE is supposed to be doing for?
I don't know, honestly. I haven't actually thought about it in that context, but it would no longer be MACE. There is no reason that you can't replace the naive model, any other model that you wanted to do. So in your case, the correct model based on that regression. For some, another project that I'm working on at the minute, we're using an age structured production model, so a really simple assessment model as the naive model. Because even though we're using the naive model and in time series forecasting literature, that's what they always use. It doesn't, to me, it doesn't feel like the most intuitive naive model, or the most intuitive baseline model to use in something like fisheries, because I think we always would have some level of data or expert opinion or idea as to what a better prediction.
Right, it seems like if you're just using what you say here, like you're ignoring past trend.
Right.
If you have it, for
Exactly, exactly. And if you're particularly with something like sardine, where you're getting these massive changes in 3 years, it's
you have some predictive skill about what's coming in next year based on just the patterns of things.
exactly, yeah.
Well, awesome.
Thank you, Becca.
Okay.
That was great.
Thanks, everyone.
Yeah, and thank you everyone for coming today, and we hope to see you next week, where will hear from David Smith on robust analytics for malaria policy and adaptive malaria control. So thank you, everybody. Happy Friday.